All right, it's now my great pleasure to introduce Bonnie Ray. She's the Director of Cognitive Algorithms at IBM's T.J. Watson Research Lab. She's also a Fellow of the American Statistical Association, and she was a tenured faculty member in mathematics at the New Jersey Institute of Technology. She has a PhD in statistics from Columbia University. Let's welcome Bonnie.
Thank you. And thank you for having me. I can't get rid of the little trouble at the bottom of my screen here. But we can get into a whole discussion about what is cognitive computing and what is cognitive algorithms later, you know, just to add to the confusion about what is data science. But I want to talk to you today about some of the types of data analysis that we do at IBM Research. And if we use some of the things that Rachel said concerning, you know, how we define data science, I would say that at IBM are more on the no, that's okay. I would say we are more on the analysis of data to really drive decision making rather than building data products, because fundamentally IBM Research is not a company that that is in the data collection business. Although sometimes we do build data products for our customers, a lot of the work that we do is really designed to drive better decision making. It's not just about analyzing the data. What's the analysis of that data intended to drive? For those of you who are not really familiar with the breadth of what we do at IBM Research, we really have expanded our research organization in the last 10 to 12 years, basically opening new research laboratories around the world, including the latest lab in Nairobi, Kenya. We also have a lab in Melbourne, Australia, in Brazil, in Dublin, and then the more older and more established labs in Yorktown Heights, New York, Almaden, California. And we really like to think of the world really is our lab. We do a lot of different things. So again, we're not really just a data science company. We do behavioral sciences, we do nanoscience and nanotech. We have core math sciences, skills in statistics, machine learning, optimization, and we do a lot of work in support of our services business. And my new role as of 2 weeks ago as Director of Cognitive Algorithms and Cognitive Computing area, I actually will have the opportunity, I believe, to do much more interdisciplinary work among the around the behavioral sciences with the human-computer interaction, bringing in machine learning, AI, and optimization, along all of that building on top of our deep QA foundational work for Watson, the Jeopardy-playing computer. But today, I wanted to just give you a couple of examples of work we have done that really spans the gamut from what one might call a data product to much more of an application to drive business decision making, and then talk about how the analysis of very, very large amounts of data can actually drive new methodologies for analyzing this data, similar to what Rachel talked about, you know, the bringing together of computer scientists and statisticians and machine learners working together can actually drive new ways of thinking about how we analyze this data. Maybe there's some new paradigms that we need to be thinking about. And then I'll talk about what's next. What's next for Watson? What's the next generation of Watson? So I'll tell you first about an analysis of data for UNICEF. So some of the work that we do is not directly in support of the business, but is really designed to work with agencies that may not have the resources to have a data science team, but IBM can come together with them to help them solve some pressing problems that could have a very big societal impact. And this is certainly not big data, but in May 2011, UNICEF actually launched what they called the U-Report system in Uganda. And so what they do is they support polls by text messaging on a range of socially relevant topics, and those polls are conducted weekly, and there's feedback sent to all of the people who have answered the polls at the end of every week. And so the responses to these polls, again, is done via text messaging. The results are parsed and summarized by location at this U-Report website. But these U-Reporters, again, these are youth, mainly in Uganda, but also in other African countries. They can also just send text messages at any time on any other issues that they would like to speak up about. So, of course, the polls themselves are very structured, but these just contributed text that they would like to bring to someone's attention could be anything. And they have about 245,000 Ugandans enrolled in this U-Report system now. Here at the bottom of the page you see a map, and this is just shows visually the outcome or the responses to a particular poll. Now, what about these unsolicited texts? Well, a lot of these texts are very important. I mean, it's really critical that they get to someone's attention and that these messages get in front of the right people, because some of them can be really heart-wrenching. Hello, you reporters. I am in Buikwi district. Let's try to prevent young girls against early marriages. It's serious here. Or dead bodies are carried on wheelbarrows and logs. No stretchers, no ambulance. Can Uganda rescue something to save people's lives? So these are the types of messages that are coming in, and there just aren't enough humans to read all of these messages and try and determine, is this something that requires immediate action? So the job that was asked of IBM Research would be, is there a way that we can just automatically parse and categorize these unsolicited text to try and identify the ones that really require some immediate action? And UNICEF had already come up with a categorization scheme for these types of texts. They had 13 different categories, and these categories actually were mapped to particular departments within UNICEF that were charged with handling different types of issues. So what you see on the top here are the different sort of policy departments, if you will, within UNICEF, and how some of these categories map to those departments. What was the real challenge here? Well, one challenge is that these class labels for these different categories are highly skewed. Really, less than 1% of the messages are such that they map into one of these categories and really require urgent attention. And UNICEF was actually doing some work themselves, just trying to do keyword matching to pull out keywords from these text messages and just map them to categories. And it wasn't doing so badly, but the question was, can we actually help to improve that against that baseline? And so we took this on and said, well, we think we can do something that's a little bit better, at least. And so the first approach that we tried was looking at more like a supervised classification scheme for, using statistical or machine learning methods. The approach really was to treat the problem as binary task instead of just a big multi-way classification problem. And we were able to improve on this simple keyword text matching, but not by a whole lot, actually. But think about text messages that, that we all send. We have many misspellings or words maybe that we didn't intend to type, but the Google correction automatically put in there for us, and we failed to catch it. Now we're talking about a mix in Uganda of probably more native language intermixed with English, and you can see how trying to do some kind of spell correction could potentially add a lot of accuracy to this problem. So the next step was to do some simple spell correction using some open source libraries to do that. And that actually improved things quite a bit. But we thought we could do better. And so we applied a novel approach here, because in this case we actually had good information from having humans who have said these particular keywords map to these particular categories, and that worked quite well for some categories like water. But it was very difficult to find a set of keywords that was comprehensive for areas like social policy. It's just too broad for a human to come up with a priori a set of keywords that are going to provide a clean mapping. And so the innovation in this particular problem was really around dual supervision. And let me just say a little bit about what I mean by that. Again, you can think of those keyword lists as background knowledge about the domain. You don't have to completely dismiss that knowledge or discard it when you move to a statistical text classifier. That background knowledge can be incorporated in this dual supervision framework. So the classifiers can be trained using labels on the examples. That's your classical approach, but also using those keywords as prior knowledge on the association of your words, your features in the machine learning algorithm to particular classes, these feature labels. And that's what we're calling the dual supervision. So really, the underlying technique is to take, to extend this naive Bayes approach to incorporate that information from the labeled features. So in a standard naive Bayes approach, you're predicting the class with the maximum likelihood for each of your extracted words that are your features. But, and the prior is estimated from your labeled examples. But in this dual supervision approach, you're actually looking at conditional probabilities estimated from your examples and from the knowledge that you have about how the keywords map to particular features. And this wasn't novel in this particular application, but it was an interesting recognition of how to take a method that had been developed actually by some of our machine learning team a few years earlier and apply it in this new application. And then, so each of these sort of steps improved the results just a little bit more. And then finally, in order to improve which messages get ranked at the top, we said, okay, we're going to modify sort of the rankings of most critical to, for someone to look at and try and address by ensuring that the texts that contain the keywords are ranked at the top. So we have what comes out of our machine learning model in terms of ranking the text within a category and which ones are the most likely to be in that category. And then we're just going to re-rank them to get all of the sort of ones where we know it contains a keyword to come out at the top. So, the keyword matching actually gives you lists that are very high precision at the top, but it's not very, those lists are not very comprehensive. So we re-rank the model results so that the messages with the keyword matches are bumped to the top of the list, and we keep the rest of the ordering intact. And that actually provides even more improvement here. And I think while this may not be a big data problem in any way in the same vein as what a Google or a Facebook analyze it, it is something that's too much for a human to do. And it is having a real impact on the lives of Ugandans. So this analytics capability has been deployed on the UNICEF U-Report server in Uganda. There's an interface to allow UNICEF partners to identify critical messages. It was deployed last fall. So a UNICEF employee can sit down and filter messages by category or action status. They can then drill down into the actual text messages and select and assign some kind of ratings to them. And just to give you an example of the impact it's having, this U-Report provided information on the influx of refugees that were fleeing fighting in the Democratic Republic of Congo. And this U-Report system was able to immediately collect and process a very high volume of text messages reporting on the condition of these refugees so that decisions could be made about how to best provide aid. So I don't know if you would classify this as a data product, but it's definitely an analysis of data that's too large really to be handled by human and is having a real, has been deployed and having a real impact on people's lives. So one of the things I enjoy about IBM research also is the fact that we get to work on many different types of problems. So this is an example of a problem that we have addressed with one of our clients or a partner. A lot of the problems we work on are with other parts of the IBM business. So I want to briefly mention some work we've done with our integrated supply chain area. And the reason I really picked this example is because it illustrates maybe a structure of data that may be unique to businesses or enterprises. And I'll talk about that in a second. But the problem statement really was that, well, first of all, IBM's integrated supply chain organization is responsible for about $35 billion, or almost half of IBM's cost and expenses. So it's a really important part of the organization. And they're trying to manage this business. They had tons of metrics, which they were trying to understand and use to manage business performance. But all of these metrics really weren't providing any insight. They were leading to inconsistencies, data overload, duplication, and what were they really trying to tell the people who had to make business decisions? So what they really were driving towards was radical simplification, fewer metrics, harmonized metrics, and rules-driven actions. And some strategic tools like performance dashboards, which really provided insight. Just weren't a whole lot of reports with metrics that people, different people really may interpret very differently. So we were asked to focus on trying to really understand which of the supply chain operational metrics were important for driving customer satisfaction. And the important thought here is that there could be some relationships among many of these different metrics, but we were interested in identifying the significant causal relationships among them. And so we applied an approach called temporal causal modeling that was based on an idea called Graphical Granger methods. And the idea really, was that we were going to find groups of metrics that were important for driving customer satisfaction, and trying, by this grouping method, we can extract the most meaningful, the most insightful relationships. But the interesting aspect, though, I wanted to point out here, because I'm not sure that this is really an aspect of data that is seen, that you get in some of the other types of technology company analysis that we've heard about so far, is the data for the business really needed to be analyzed. It's structured in a hierarchical way. So you may be interested in, at the level of the US, or North America, what are, how do the key operational metrics for North America's drive customer satisfaction in North America? But you could bring that down to the next lowest level and say, well, North America is Canada, US, and Mexico. What's going on in the US, is that the same as what's going on in Mexico? And are the same metrics driving customer satisfaction in the same way? And so this idea of hierarchical modeling, I think, is something that's really important, at least for modeling different aspects of IBM's business. And how do you do that? How do you leverage that multidimensional hierarchical structure in the modeling? Should you combine everything, like all of the data for North America? Should you impose the same kind of structure for these relationships in the US as you do in Mexico? Or should you let each entity stand on its own and have its own sort of relationships? So I'm being told that I have only 0 minutes here, so I did want to just talk about, so the problem I just talked about was large data. Maybe it's not, again, it's not the massive scales of data that other tech companies are dealing with. But we are doing some work on a fundamentally new approach to what I'm calling making big data small. And this is an idea of what's called sketching. Just think of it as a random sample, although a very smart random sampling of your data, and then analyzing that randomly selected data. And you can prove that you can get bounds on how well the analysis of that smartly randomly sampled data actually matches what you would get if you had analyzed the entire data set. And I think this is very powerful. And the work that we are doing specifically is to expand some of those ideas to kernel regression, so non-parametric modeling. Think about it, if you have huge amounts of data, you can't even think that any of these assumptions that we might normally make, say in applying a linear regression model, are going to hold for all of that massive amount of data. Why aren't we doing non-parametric modeling? Well, because it's more computationally intensive. Well, if we can use some of these sketching techniques for non-parametric algorithms like kernel regression, then we can start to apply non-parametric methods to these massive amounts of data. So that's some of the work that we're doing now. And then just to finish off, what's next? Well, the era of cognitive computing. So about 2 weeks ago yesterday, IBM announced that it's establishing a new group within our software business focused entirely on building out the capabilities of Watson, the deep QA system. And it really is designed to bring to market this new class of software, services, and applications that think, improve by learning, discover, answers, insights to complex questions from massive amounts of big data. Because now we're not dealing with just data that's generated once, but looking at how maybe a human is interacting with a system and learning from that data. And so that is my new job, is to lead the team that is charged with developing the algorithms that will support the broadening out of the Watson capabilities. And we have a brand new building that'll be opening soon down in the East Village of Manhattan to support this effort. So, thank you.
We only have time for one question while the next speaker sets up.
In the SMS problem, a lot of what we do in these data problems is trying to find things that apply to clusters of data. But a lot of what seems to be a really hard question is, what do you do in trying to identify very unique single messages that actually may be critical to the life of that person or the life of that small village or whatever, but you may only have one of those, right? What do you do about that problem?
Oh, it's cut off too. Yeah, I know. Let me.
For that problem, I mean, we were really trying to rank the messages in a prioritized order so that now you've reduced the problem for a human. A human still had to be in the loop, but he's not going to have to look at 1,000 messages a day. He may only have to look at the top 10 in each of 13 categories and identify which are critical to take action on.
It's usually an option there.
Yeah, extron scalar.
We can take another question while we're waiting.